Okay, hello. I think that we're back. I am continuing the last stream. It looks like my computer just crashed. Unfortunately, we have to start a new stream, but that's fine. So, this will be two separate videos that are uploaded. And whatever. Let's just keep going. So, what we're doing is we are proving the fundamental theorem of arithmetic. I'm just writing down the proof verbatim for the sake of trying to learn and memorize this proof. I'm pleasantly surprised that it doesn't have as many prerequisites as I thought, but we do have one prerequisite that I just came up to finally. We proved, first we proved existence by mathematical induction. Now we're in the middle of proving uniqueness. And I see that it's a mathematical induction and a contradiction. So you need those two proof strategies. And right now, in the process of writing down the contradiction, the contradiction is going to rely on a corollary that we haven't yet seen. So we're finally getting to a prerequisite that we haven't gotten to yet in our journey. And that's okay. Hey, Patricia, good to see you. So the last stream just crashed, and I am trying again. We'll see what happens. All right, so math, iPad horizontal plus Sony, air server. Okay, so we got the iPad back up on screen. How's it going, Patricia? I hope you're enjoying this stuff. I don't know if you've seen the last couple of videos on proofs and introducing proof strategies. I know you saw some on induction before. Yeah, for the sake of, since this is a separate video, let's repeat what we're doing. We are proving that every integer can be uniquely written as a product of primes. Like, for example, we have a table. Like 4 is 2 times 2. 6 is 2 times 3. It can also be written as 3 times 2. But as long as you require that the primes are increasing, then this is a unique factorization. 7 is prime, 8 is 2 times 2 times 2, 9 is 3 times 3. And so, in a sense, we're really proving this fundamental theorem of arithmetic, henceforth FTA, that primes are like the building blocks. They are the atoms of the numerical universe. Primes are the atoms. I guess that's why we call this like the fundamental theorem of arithmetic. So this statement says for every number there is a factorization of into primes, and this factorization is unique. Okay, so in the prior part of this video, we established existence, and now we're going to be proving uniqueness. Uniqueness. And something that I thought was awesome, super cool, that's going to stick in my head is that you don't need anything more than mathematical induction and the definition of a prime. You need strong math induction and the definition of primes to prove existence. So that's pretty cool, I think. Now, to prove uniqueness, we need some heavier machinery. So we're copying this out. To complete the theorem, we must establish uniqueness of factorization. Again, we proceed by mathematical induction. Our table also tells us that the factorization of each number less than or equal to 12 is unique. Assume that each integer m up to some number, like some number of dominoes have toppled over in our inductive hypothesis, assume that every number up to k has a unique factorization. Suppose that k plus 1 has 2 prime factorizations. So now we're coming up to a contradiction, which is a different strategy, and it's easy to explain, but it is new in this series. So suppose that k plus 1 has two separate factorizations. Since q1 divides k plus 1, we see that q1 divides the first factorization into primes p. Therefore, q1 divides pi for some I by corollary 2, 4. Okay, so I'm not going to write that out for the sake of time. I do have to, run kind of soon, so I just want to try to get through this proof and maybe a problem. But yeah, here is the first prerequisite. The first real number theory prereq to getting to FTA. And this is going to help me memorize all this. Since both Q1 and Pi, for whatever prime that is, Pi, are primes, since both are primes, we conclude that Q1 equals Pi. Okay? So that's a definition of primes. If two primes... If a prime divides another prime, then they have to be equal. That makes sense, I think. Clearly, we may reverse the preceding argument to show that P1 equals P... no, I'm not using this notation. I'm using this other notation. Qj for some j. Hence, P1 equals Qj greater than or equal to Q1. And Q1 equals Pi greater than or equal to P1. Therefore, P1 is greater than or equal to Q1 greater than or equal to P1. Yeah, okay, wait. P1 is greater than or equal to P1. Where? Oh, yeah. All right, so P1 is greater than or equal to Q1, and then Q1 is greater than or equal to P1. I just misread something. Okay. Yeah, so P1 is greater than or equal to Q1, and Q1 is greater than or equal to P1. And so P1 equals Q1. Thus, k plus 1 divided by P1 is an integer not exceeding k. And P2 dot 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 Pu, the last of the P's, is k plus 1 over P1, and that is the Q's, Q2 through QV. Hence, by the induction hypothesis, okay, U equals V, Q2 equals P2, dot, 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 and QU equals PU. Thus, the fundamental theorem of arithmetic is established. That's nice. I like the finality to that. Thus, the FTA is established. Ooh, and I'm noticing he draws a filled-in square for that one, and I feel he's been using empty squares previously. Or maybe it was the other book that used empty squares. Nope, yeah. Q1 equals P1. Yeah, we got that. We absolutely got that. Also, nice to meet you, Godex Sigas. How are you? Yeah, neat. Yeah, I got that right here. So we just keep chomping off one prime at a time inductively. Like, we showed P1 equals Q1, and then the same argument is going to show that P2 equals Q2, and then P3 equals Q3, dot, dot, dot. They all line up and match each other. And so, since they all equal each other, then the theorem is established. Yeah. Cool. All right, so there's a proof, and that is the goal of the week, which if we summarize this proof for my own head to try to memorize this proof. Summary. This was pleasantly easier than I remembered, because it's been a long time. I'm dusting off cobwebs. I took a number theory class. I feel it was weeks into the class that we got to FTA. And I feel like the proof was like a little bit more cumbersome. It was like a lot fiddlier. It was like a lot more tedious in the other book, which I have over there, Rosin. I feel like this was a much simpler, nicer proof that I'm going to be able to remember forever. The summary of the proof is existence and uniqueness. Existence by mathematical induction, strong mathematical induction. I think that's important. And then uniqueness is mathematical induction. I think we use the fact that it's strong. I'd have to double check. Maybe we didn't. We didn't really use contradiction, did we? I thought we were going to. No, yeah. Suppose that k plus 1 has two prime factorizations. we did not actually... Yeah, no, we don't need contradiction. I was wrong. I was completely wrong. Mathematical induction, and then if you take two factorizations, you can prove that the two factorizations are equal. And we require a corollary, which really is like if a prime divides AB, then the prime divides A or the prime divides B. I think that that's what this corollary is going to say. So this was a to-do that we added. What is this prerequisite? This is like a requirement. It's a prerequisite before you can prove FTA. But it is a huge takeaway for me that you can show existence of factorizations with nothing more than induction. So it could be a exercise. That's cool. I've never known that before. All right, so let's find out, just for completeness, what is corollary whatever? Corollary 2-4. So that's in the prior section. Nope. There's something I don't like about his organization. Wait, Theorem 2-3, Corollary 2-2. What the heck? He doesn't actually name a Corollary 2-4. There is a Theorem 2-4, so I think that it's a typo. I think. Unless it's in the exercises. What's going on? By Corollary 2-4. I think he wrote Corollary 2-4. Or he's referring to something very subtle in Theorem 2-4. Really? Really? Are you for real, Mr. Andrews? I don't see... This isn't exactly the theorem that I was expecting. So I'm getting confused. Oh, no. Here's Corollary 2-4. Yeah, I don't like his notation. Because there's like a Theorem 2-4 as well as a Corollary 2-4. So the numbers are not unique. Like I would... anyways. Let's not get into a tangent there. Corollary 2-4. This is the fact that we required. If P divides A1, A2, ... AN, then there exists some I such that P divides AI. Okay. So, if P divides a product of integers, then there is some integer in that product that the prime divides. All right. If we keep working backwards, corollary to 3, these are both corollaries of a theorem. Corollary to 3, if A and B are integers, P is A prime, P divides a product of numbers, and P divides, if P does not divide the first of those two, then P divides the second. Okay, so that's really close to what I wrote down as like what I expected our requirement. What I wrote down was this, that if P divides AB, then P divides A, or P divides B. So we're getting close. So I wonder if the corollary is based on what I expected. No, all right, so, or the theorem 2-3, that the corollary is a result of, is if A, B, and C are integers, where A and C are relatively prime, and if C divides AB, then C divides B. Okay, so, no. Hey, Math Spellbook, good to see you, man. Yeah, you caught this live stream. Also, good to see you, Jeffrey. Thanks for tuning in. All right, now we're getting into territory where we do require more and more things, because we haven't yet defined what does relatively prime mean, what does dividing something mean. So here is there's going to be more and more math facts and statements that we need to prove in between. In fact, do we need the definition of division in order to get existence? I don't think we use division at all. Like, for existence, you just need... Yeah. Existence does not depend on very much, but uniqueness depends on a bunch of stuff in between. So that's cool. That's really cool to notice. So I wrote down that it requires this, which then is like kind of a restatement of that corollary, which then requires that if C divides AB and the greatest common divisor of C and A equals, if they're relatively prime, then C divides B. Was that correct? Did I get that right? If A, B, and C are integers, where A and C are relatively prime, and if C divides A, B, then C divides B. Yeah, so I got it, right? If this and this are true, then C divides B. Did I get that right? Yeah. Okay, so now I have an idea of the requirements in order to prove FTA, which is neat. Our goal is to meet in the middle and prove all the theorems from the left, memorize the theorems from the right, and then meet in the middle somewhere. So we copied the proof. We actually understood way more than I expected for the proof of 2, 5. And now, if I have a little bit of time, I could try to tackle an exercise. Solve an exercise? Question mark. All right, Math Spellbook asks, what are we trying to prove here? Yeah, you just tuned in. So what we are proving is the fundamental theorem of arithmetic, that every number can be uniquely written as a product of primes. My way of saying that I like to rephrase it, is that the primes are the atoms of all numbers. That every number is uniquely written as a product of primes. Like, here's this table. For all the numbers up to 12, we can see that there's exactly one way to write 6 is 2 times 3, or 2 times 5 is 10. We don't consider the second one to be unique because it's unique up to reordering. So as long as you assume that the primes are strictly increasing, or as long as you assume that the primes are increasing, then it's unique. So uniqueness up to reordering is a way to say it. Yeah. Cool. All right, so let's see. Can we tackle an exercise? Now's a good time to say that Math Spellbook, I don't know, did you say that do you have this book? Did you get this book? We are tackling exercises from this book. This number theory series is teaching proofs and proof strategies, like intro to proofs, as well as number theory, like applying proofs to number theory. So it's up to you. We could tackle like a truth table or something like that from here, or we could try to take a look at an exercise from number theory. What do you say? It's up to you. You're on the spot. What do you want to see? Some proof theory, or like proof strategies, or do you want to see a number theory exercise? I'm going to give you 10 seconds before I make my own preference of choice. Yeah, let's do proofs. All right, cool. So, How to Prove It by Velleman. Let's do it. So, I tackled a couple of yesterday. I'll probably, since you are here, and you weren't here yesterday, I'll probably do something similar. So we've already done Velleman 0.3. This was about Euclid's proof of the fact that there are infinitely many primes, and how Euclid's proof is a way to generate a new prime given a list of numbers. Find 5 consecutive integers that are not prime. I don't like chapter 0 because 0 is like an introduction, and it does not. These are kind of calculation exercises. I want to jump to logic. Let's do a logic problem. Let's just do the first one. Why not? I gotta go. I gotta run. All right, so analyze the logical forms of the following statements. Let's see. I gotta go, y'all. Okay, analyze the logical forms of the following statements. A, we'll either have a reading assignment or homework problems, but we won't have both homework problems and a test. Okay, so I'm going to call having a reading assignment. I'm going to say have a reading assignment. B is have homework problems. And C is have a test. We have three things. Have a test. Okay? So then we'll have either a reading assignment or homework problems. This will have either a reading assignment or homework problems. That is like one clause, which is A or B. And then we'll have either... We'll have either a reading assignment or homework problems. This is all one long clause. But we won't have both homework problems and a test. So this thing is true, and this second clause is also true. We won't have both homework problems and a test. So we won't have both homework problems and a test. So the negation symbol in Velleman is this like kind of bracket. We won't have both homework problems and a test. It's not true that we'll have both B and C. I think that that's the right logical form of that sentence. I think so. Let me know in the comments if I'm wrong. You won't go skiing. I'm going to call A. Or you will, and there won't be any snow. I'm going to call B, there will be snow. So then, if there won't be any snow, then that's not B. So this part B is saying you won't go skiing, or you will go skiing, and there won't be any snow. Okay? Part C, square root of 7 is not less than or equal to 2. How do you form that? I think that you want to just say that this is like not A, where your proposition is square root of 7 less than or equal to 2. And then this is like, yeah, I think that that's what you want. This reminds me of a college course I took, Logic of the English Language. This is exactly that. This is exactly logic. You can take logic to be super mathy, or you can try to take it to be somewhat informal. So this is symbolic logic, which tries to capture like conventional logic into symbolic form. And I was saying yesterday, also I'm glad to see that you're still watching, Patricia. I like this series, the number theory series, may become number theory and foundations. So you can study logic, and that's kind of this math that underpins all math. And it's like really closely related to philosophy. So we may take proof theory and keep going further down into foundations. And then there's really beautiful math, especially Gödel's incompleteness theorem, which exactly uses the fundamental theorem of arithmetic that we just proved today, which is dope. Like, and it is kind of like the quantum mechanics of math, and I won't get into it right now. I might say the square root of 7 is greater than 2. Exactly. So that is also true. And that is, yes. Yes, like you could also say that. Or B, square root of 7 is greater than 2. Like that could be your other proposition. A, not A, is tautologically equivalent to B. The two are two different statements of the same thing. All right, so there was one exercise. Let's get a problem from section 2. We already did this first truth table problem. Now let's get the second one. Truth tables. So this is kind of easy. I'm kind of cheating. I don't want to say I'm cheating, but like these are not the hardest. These aren't really proofs. This is more understanding this logical structure of mathematical statements. But I think it's really important to see this stuff. So A, this one's getting more complicated than yesterday. All right, so we've got two things that are either true or false. I like to use 1 for true, 0 for false, and 0, 0. Okay? Then if we build this up slowly, we need what not P is. Not P is 0, 0, 1, 1. Then we need what Q or not P. What is Q or not P? So we take a look at the second and third columns, and we OR those two. And then we need P and Q or not P. So now we are ANDing the first column and the fourth column. Okay, so we're ANDing those two. First one is true, second one is true, first one is true, second one is false. Then all of these are like that. And then we're negating all of this stuff. So I'm running out of space here, but we're negating that last column. So 0, 1, 1, 1. There's our truth table for that whole thing. And you can drop the middle columns if you want to just have the final result. But it's good to show your work, right? PQ 1, 1, 1, 0, 0, 1, 0, 0. Now we have P or Q. P or Q is this. We also have another thing called R. Let's just add it here. Okay. No, let's do this carefully. Let's start over. P, Q, R. Each of these can be either true or false, so there are 2 to the third possibilities. Oh, meeting has ended. Oh, no. Did I... Shoot. Oh, well. Yeah, true and false. I know. I like 1 and 0. Sue me. Sue me. I like 1 and 0. It's easier for me to distinguish the propositions from the truthity of the two. If they're all letters, it starts getting confusing to me which is which. They're different like categories or something, right? Okay, so those are the cases when P is true. I think I got them all right. Now P can be false. And there are 8 cases when P is false. There are 4. And now again, we can rewrite the possibilities of Q and R, so just focusing on that segment of the matrix. 0, 0. I don't know why the Zoom meeting ended. Oh well. Not P. 0, 0, 0, 0, 1, 1, 1, 1. Oops. Well, yeah, we did need not P. We need maybe not P or R. For some reason, I'm starting on the right of this final equation that we want, or final compound form. Not P or R. So we are ORing the third and fourth columns. 1, 0, 1, 0. Not P or R. 1, 1, 1, 1. Okay, not P or R. And then let's get this first term, P or Q. So we're ORing the first two columns, 1, 1, 1, 1, 1, 1, 0, 0. Right? P or Q is like that. And now we are ANDing those two terms. I'll write out the whole thing. P or Q and not P or R. Okay, so we are ANDing the sixth column. We're ANDing that with the fifth column. Okay? So 1, 1, oh wait, no, whoops. 1, 0, 1, 0, 1, 1, 0, 0. Cool. So that's a pretty complicated mathematical statement. Yeah. I forgot how much I love truth tables. They're very, truth tables are very meditative, or just, they're things that are just satisfying to write out. I've forgotten how much I like them too. It's just fun to write out a whole truth table by hand like this. Too bad that you don't ever need to do that in the real world. Like even in mathematical proofs, you're not really writing out truth tables very often, but this is a way for you to really practice and understand like these compound English sentences and like with like nested clauses, and either there are infinitely many primes or blah 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 whatever. Yeah. With a background in CS, you live and breathe zeros and ones. Exactly. Like, quite literally, like, this is how computers implement logic gates. And logic gates are literally logic truth tables, just like this. And it's very, very useful to use 0 and 1. Yeah, super useful. But I didn't want to get into that. Yeah, like, electrical engineering, you actually do learn this. This is applied and useful for circuits. It's incredibly useful for circuits and for building a computer. So this is not just for pure math, for playing chess, for like doing math in and of itself. This is actually used by computers, which is great. Yeah, I can use truth tables in the real world to help make decisions. I'm glad I've never needed to make such a complex decision that it has required me to write out a truth table for it. But if you squint, probably some spreadsheets that I've looked at for like project management are essentially truth tables if you squint. So anyways, this was fun, everybody. I have to run. I have an appointment. I gotta go. Thank you for watching. Maybe it's okay that this video is split in two, because shorter videos are probably better. My handle is the Math Hobbyist. If you enjoyed this, no expectation, but there's a tip jar out there. Thanks, the Math Hobbyist, mathhobbyist.com. I'd love to do this stuff, honestly, like full time. Like, I think it would be amazing if I could just record YouTube videos and do this full time. So, no pressure, but for your consideration, would appreciate it. That's one way to say thanks. Another, like and subscribe, y'all. Like, I know that some people are watching these after the fact. If you made it this far, you must enjoy this content. Let me know. Let me know what you like about it. Let me know what you want to see more of. That helps a lot. That is a really great way to say thanks, for this time and for this video. So, positive vibes to you too, Math Spellbook. Thank you. Positive vibes, lights, wishes, energies, and unexpected wonders to everyone. Take care. Yeah, take care. Thanks for swinging by. It's fun to hang out with folks while I do this. All right, cheers. I'm going to go. Bye.